Welcome to today's coffee lecture, which is about the search of coordination compounds in Reaxys. And of course, I quickly want to introduce what is Reaxys because there's not only coordination compounds in there. It's a database for chemical information. It's one of the two big ones. So the other one is SciFinder, its competitor. In there, you find structures, you find substances, but also for these substances, you often have attached data like properties, chemical, physical properties, reactions, and then, of course, the links to the corresponding literature. Reaxys is owned and developed by Elsevier, one large publishing company. Other products from them you might know as Scopus, Science Direct, Embase, or Mendeley. And now I want to go straight into what the problem actually is. So let me quickly move over to ChemDraw. Here I have drawn a salt. This is called size salt. And the problem with the search of organometallic or coordination compounds is that actually for the human eye, we draw the things slightly different than the database understands it. So here, for example, we have a complex to this ethylene. So this is pi bonded, and we just sort of stick it on top. And there we go. And now I'm going to copy this part so I can copy that easily into the database. That's maybe also, if you're not aware of that, you can copy as and smiles. And now we move over to Reaxys. And here I can draw my own thing, but I can also insert it. And this works very nice if you have a normal organic molecule. But let's see now what happens if we do this with this coordination compound. And then you see that we have sort of the individual components listed. And I'll quickly remove that, the potassium, because we're going to search as drawn, and then we will get some salts and so as well if there are any hits. So let me quickly perform the search, and we see that we don't find anything. And that is, of course, because this is not drawn correctly. Here we have a methyl compound. And the way we need to do this is we need to consider the delocalization of the bond, because this is pi bonded. So basically you have a partial bond to either of these centers. And the way we have to do this, so I'm just going to delete this group here. Here under the bond tools, we find a function for single or double bond. And that is the one we need to use for this bond here. That is now sort of a partial bond. And for the bonds that connect to the metal, we need plain single bonds. If you use anything like in different editors, you have functions like dative bond or something, don't use them. The database will never understand them. So now we can search again. And then you see that we actually find this ethylene complexes, and they are then drawn. So for example, here we have a double bond. If we go down, typically it's this platino cyclopropane propene that we have here. Okay, now we want to go one step further. Of course, I could search for something a bit larger. Let's say I have an allyl complex, and then I would do the analogous thing. So I just draw it that way. And then I have delocalization over 3 different carbon atoms. And we can search that as well. And then for this example, now I just have 1 hit, but let's look how it's depicted here. So here we have one of them now is a double bond and one is a single, and they are all connected to the central atoms. So that is what you need to know to search for these delocalized things. You can also extend that. So typical other ligands are cyclopentadienyl. So there you have a five ring where you all these bonds need to be the single or double, and each of the centers need to be connected to the metal. Okay, now something that also pops up a lot in organometallic chemistry is bridged things. So here I'm going to search for some palladium, and then I can simply copy here part of the structure, and then I rotate it around. It's still going to be understood, of course, And then I want my bridging atoms, and I just move these on top of each other. And so you see they are highlighted in red because it's an unusual valence, but it's still in a way that the system understands it. So you can simply ignore that. And now let's see what we can find this way. And you see I have one entry, for example, exactly this complex. If we look at the formula, we see that it fits. The structure here is not so nice, and that sometimes just happens. You sort of need to tease out what's actually going on. But we see that there is the bridging chlorine atoms. So this at least is true, and we also see that we have drawn the allele bit, so that should work. Now, sometimes you are very open to what you will find and don't have so many restrictions. So I want to show you an example of what other things you can do to maybe be more flexible in your search. So one of the most important functions is this S-max here that we find on the left side. And that basically opens up positions for substituents. So here I could say for this palladium, I can have any number of substituents here, and I say as drawn, so I don't allow substitutions here on the allele. And so let's see what we find then. So we have palladium allele, and it's just a plain allele, and we have the chloride and whatever else we find, and then you see we have some 700 compounds. We can look at what those might be. Then we have, for example, here N-heterocyclic carbenes with an allele. We have the chloride. Here we have a triphenyl phosphenone, and so on. Now maybe here I've explicitly drawn the chloride, but maybe I don't really care about that. I could allow for any halogen. And there's also an option for this. So here on the right side, we have a bunch of atoms, but we also have this A. And if we click on that, there is further options, and one of them is the X here, and that stands for any halogen. So I could say, oh yeah, here, I don't care what the halogen is, it could be any. And then we can do the search again, and you see we found some 50 more compounds. So we also have the bromides, the iodides, and potentially the fluorides, which probably are fewer included. And then what else do I want to show? What could also happen is that maybe I don't want to restrict to palladium, but I think, oh yeah, I'm interested in the whole group 10 metal series, or at least the first 3. So I can use an atom list and say, oh yeah, nickel, palladium, platinum. I take all of these and I add them here. And then now you see that this S6 that was there has disappeared. So I need to add that again to open up the position to allow for additional ligands. Because if I don't do that, then I only have 2 ligands. I have the chloride and I have the allele. And so let's see what we find there. And then we have a couple of 1,000 complexes or so. And now one last thing, what we can also do, let's say I have an additional ligand that is maybe a bit ill-defined. So let me say, yeah, I just do phosphine or 2 phosphenes that I stick on. And here again, I say, because if I search it for this, it would be plain phosphane with the hydrogen atoms. And that is not what I'm interested in. I want some organic phosphines. So here I also need to put that S6 to open up the position. And then I could also, here I have more options. No, it's up here. If I draw it like this, I would also retrieve the chelating ligands. And if I say I want 2 distinct individual phosphines, then I need to switch off these additional ring closures. But let me search that now and then get a few hits. For example, here this chelating phosphine. Here we have a nickel complex with bromide, and so on. So with that, I think I'm almost at the end. I just want to highlight that we have a digital coffee lecture card where you can find some of the information. I'll just show the link again in the last slide. And tomorrow, my colleague Gina Canarosi is going to be talking about AlphaFold for the prediction of protein structures and the latest development in that field. And with that, I want to thank you. And then for those of you who join us digitally, I quickly want to pop the link in the chat. Okay. Do you have any questions to this topic? Is there anything else you might be interested in? Also, if you join online, feel free to unmute and simply ask. Okay. If not, then I thank you for your attention and I hope we see you again tomorrow. Thanks. Bye-bye.